Hello, this is a video from Flipped Around Physics on energy and power in circuits. Okay, here we have a simple circuit consisting of a battery and a bulb connected with wires, and we can see the charges flowing around the circuit. This is a very nice simulation from PhET at Colorado University. An electric circuit is just a means of moving energy from one place to another. In this case, we're moving energy from the battery to the bulb. Charges passing through a battery are picking up energy, and then they're carrying the energy and they're carrying it to the bulb, and then they're giving up their energy to the bulb, which then gives out light and heat energy. Okay, what I've done is I've drawn a diagram of the circuit we've just seen animated, and I've included a voltmeter across the bulb. What we find is that the voltage of the power supply is a measure of the energy that the charges pick up, and the voltage across the bulb is a measure of the energy given up by charges. A 12-volt battery means that for each coulomb of charge that passes through the battery, a coulomb of charge will pick up 12 joules of energy. We write voltage equals energy per charge, or energy per coulomb of charge. Okay, so this E is the energy, and the Q is the charge. So a 12 volts means that each coulomb carries 12 joules of energy. Okay, so when the charges pass through the bulb in the circuit, energy is given up. Okay, and this 12 volts means that for every coulomb of charge that passes through the bulb, 12 joules of energy is given up. So we write the potential difference, okay, which we measure in volts, is the energy given up per coulomb of charge, energy over charge. I've now drawn a circuit with two components in it. So in this case we have a lamp or bulb, and we have a resistor. And I've also shown the potential difference dropped across both. And what we find is that again, charges pick up energy as they pass through the battery, and in this case they will pick up 12 joules per coulomb of charge. So for every coulomb of charge that passes through, it will pick up 12 joules. And that charge flows around, and then in this case the charges will then give up their energy first to the bulb, okay, and then the remaining energy to the resistor. In the case of the bulb, the energy goes to produce heat and light. Okay, in the case of the resistor, the energy goes to heat up the resistor and the surroundings. 8 volts here, the potential difference of 8 volts means that for every coulomb that passes through the bulb, we have 8 joules given up, 8 joules per coulomb given up. And for every coulomb passing through the resistor, we have 4 joules for every coulomb of charge. Power is how quickly energy is given up. Okay, so for example, if we have we measure power in watts. If we have a 60-watt bulb and a 100-watt bulb, then we know from experience that a 100-watt bulb is going to be brighter. It's brighter because it's giving up energy more quickly than a 60-watt bulb. In fact, a 100-watt bulb means that the bulb is transferring 100 joules of energy from electrical energy to light every second, so 100 joules per second. Whereas a 60 watt bulb, of course, is transferring 60 joules from electrical energy into heat and light, so 60 joules per second. The power, electrical power, is energy per second, so energy in joules divided by time in seconds. Turning to our simple circuit with a battery and a bulb, we can see a current flowing around the circuit, and current is just the rate of flow of charge, so it's charge per time. So this is the charge over the time in seconds. And as we talked about previously, the potential difference dropped across the bulb is the energy given up per coulomb of charge. Now let's, just for interest, let's multiply the potential difference dropped across here times the current and see what we get. So what we can do is I times V equals, if we take I as Q over T, and then we multiply that by V, which is E over Q, you will see that the charge cancels, and we end up with energy over time. And energy per second, energy over time, is the power. Okay, so let's have a look at an actual example. So in this case we have a battery connected to a bulb and a resistor, and in the circuit I've drawn in that we have a current of 3 amps flowing. In this particular case we've got, if we measure the voltage or the potential difference across the bulb, we get 5 volts, and when we measure the potential difference across the resistor we get 7 volts. Let's use our relationship, the power equals current times voltage, to find the power output from the bulb and the power output from the resistor. Remember, this will produce heat and light, the bulb will produce heat and light, and the resistor will produce heat. Okay, so let's just do a calculation. So for this particular one, the bulb, we have that the power output equals power of the bulb equals current times the potential difference dropped, okay, equals 3 times 5. So we get 15 watts. And we could do the same for the resistor. Okay, the power of the resistor producing heat equals I times V equals, again, the same current, 3 times 7 equals 21 watts. So what we're saying is that the energy given out per second by the bulb is 15 joules per second, and the energy given out by the resistor as heat is 21 joules per second. Of course, that power must have come from our battery, so we can also find the power supplied by the battery just using the same formula. In this case, P of the battery, the power supplied by the battery, equals the current times the voltage on the battery. So that's going to be 3 times 12 equals 36 watts. And you can see that 36 equals 15 plus 21. Okay, so basically which is the power of the bulb and the power of the resistor. So essentially the power supplied by the battery is then given out the power output of the bulb and the resistor.